We previously related the kinetic energy per molecule and temperature. Now let's go back and think about how this relates to thermal energy. This is related, but certainly slightly different. And again, we're going to start here with monatomic gases, and then we're going to describe the equipartition theorem, which is necessary to talk about this outside of monatomic gases. So our thermal energy is simply the kinetic energy on a microscopic scale. So we can take the kinetic energy of every single one of our molecules, where we assume that there is n individual molecules. Now, a different way to write this is simply that you would have n molecules times your average energy, since your average energy would just be the sum of all of them divided by n. So our thermal energy is simply going to be number of molecules times the average individual molecular energy. Now, since we found before that this E average was equal to this 3/2 kBt, we then just multiply by n to get thermal energy. Now, this was again number of molecules or number of atoms. We can instead rewrite that with our other coefficients if we want to talk about number of moles, and then we have R. So depending on which format you use here is simply a case of whether you want molecules or moles. Now, the reason that this is only relevant for monatomic gases is that we're only considering translational energy, right? We've said that the kinetic energy is just how they're zooming around. We've talked about their velocity, their RMS speed. We have not talked about rotational energy. And in fact, if you know a little bit of chemistry, it doesn't really make sense to talk about the rotational energy of an atom, right? From a physics point of view right now, we're saying that they're point particles, so they can't have rotational energy. But when we talk about different types of energy, that's why we need to change this a little bit. So I just want to point that out now, but we'll talk about that in detail next. Now that we have a relationship between our thermal energy and our molecular kinetic energy, which we related to temperature, we now can actually understand a little bit better where specific heat comes from and where these coefficients, why they seem to be pretty much constant. So now before we had that our change in thermal energy was equal to n, where this is now the number of moles, this molar heat constant, and then our change in temperature. So we had that before. Now we said that thermal energy is equal to 3/2 nRT, where this is again the molar form of it, and so a change in thermal energy can just depend on a change in T. So now if you look at this, I see that my T is here and there. My thermal energy is on the left side in both cases, and then my N is here. So what I'm left with is CV on top, and then 3/2 R on the bottom. So these two equations have a lot in common, but a little bit different. So we're left with CV for a monatomic gas must be equal to 3/2 R. Now, R is just a constant, so you calculate this out, and it's 12.5 joules per mole per Kelvin. And what's a little bit interesting here is that if you look at the table of monatomic gases, back when we introduced this constant, they really had this value, and the monatomic gases were all the same. So previously, this was a value that you could perhaps experimentally measure, but we didn't actually know why all monatomic gases had the same value or why it was this value. And now we actually see, we've taken our microscopic explanation of how temperature and thermal energy relate, and we can go back to our macroscopic definition that really just shoved this parameter in there that depended on the gas, and there you go. We see now how they're related. The final thing to remember is that this molar specific heat was in fact different for diatomic gases compared to monatomic gases. So far this derivation we've done has only been for monatomic gases, so next we need to generalize to other types of substances.